Hi everyone, welcome to week 2. Now that we've finally covered electric charges, electric fields, electric forces, and electric potential, we can finally move on and actually talk about what's, I guess, probably the single biggest application of these concepts, which is electricity and circuits. So basically the foundation of modern society. So we'll start with the basics today. We'll move on to increasingly sort of in-depth analyses as we go on. But first of all, here you can see Pablo wondering what I'm doing. He's looking at me like, what's wrong with you? Hi, Pablo. Okay, that's enough. All right, so let's get started. How do I stop this thing? Where's the button? Oh, here we go. You're probably already aware that the term electricity refers to, in some sense, the motion of electric charges. But what could cause that motion in the first place? So let's consider, to start with, a simple example. Let's consider two identical pieces of metal. And let's imagine that each piece has been charged, and charged differently. So let's consider one that has a greater density, if you will, of negative charges than the other. Forget the fact that they would repel each other. Let's imagine maybe they're like bolted down to the ground. But more importantly, let's think about the electric potential in this circumstance. So we established that negative charges create negative potential. Well, the charge on the left is more negative than the charge on the right, which means the potential at the charge at the created by the charge on the left will be more negative than the potential created by the charge on the right. Instead of referring to the electric potential as more negative on the left and more and less negative on the right, instead we call the electric potential on the left low and the electric potential on the right high, because the potential on the right is higher because it's less negative than the lower potential on the left. If we want to compare this to gravity, we could say that the left represents a hole, for example, that is deeper than the hole on the right. Now let's connect these two pieces of metal by a conducting wire. Remember, a conductor is something that allows charges to move freely through it. So what will happen to the charges now? Well, on the left piece, we have negative 10 coulombs. That's a lot of negative charge. On the right-hand side, we don't have quite as much negative charge. Now we know that negative charges repel each other, but the negative charges on the left side are going to repel each other much more strongly than the ones on the right side. And so some of the electrons are going to be pushed from the left piece of metal through the conducting wire into the right. We can arrive at the same conclusion if, instead of using the concept of repulsion and electric forces, if we look at this in terms of the electric potential. On the left, we have a bunch of negative charges at low potential and a bunch of negative charges at higher potential, or rather, we have a region of low potential and a region of high potential. But if you recall the previous lesson about electric potential, we established that negative charges tend to be pushed from low potential to high potential. So the electrons over here are already at high potential. They're sort of where they want to be. But the charges, the negative charges, the electrons on the left-hand side are at low potential, and so they are going to tend to be pushed towards the high potential side. But to what extent will this happen? When will charges stop flowing from the left to the right? For example, eventually, if I pull all negative 10 coulombs worth of electrons over here and I move them all to the right, I have no charge over here and all my charge concentrated over here, and I think it's pretty clear that shouldn't happen. So when does it stop? As I pull charges from the left and move them to the right, the charge on the left becomes less negative, and the charge on the right becomes more negative, which means the potential on the left becomes a little bit higher, and the potential on the right becomes a little bit lower. Every time more negative charge flows from the left to the right, the difference between their charges, and therefore the difference between the potentials at either end, decreases. Until eventually the charges have equalized, there is no difference between the left and the right, there's no difference in potential between the left and the right, and so there will be no more flow of charge. Reverting back to the original case, this is essentially how we create electricity. Through a variety of different possible mechanisms, we create a potential difference between two locations, and that potential difference drives the flow of charge from the lower value of potential to the higher value of potential. Just to be thorough, there are different ways that I can have lower potential on the left than on the right. So, for example, here I have negative 10 coulombs and negative 2 coulombs. But I could also have, for example, positive 2 coulombs on the left and positive 8 coulombs on the right. In this case, the left is still lower potential than the right because the left has a smaller positive charge than the right does. And while it might not be as immediately obvious that the electrons will flow from the left to the right in this case, they will. So first of all, the potential rules tell us so, but also here I have only plus 2 coulombs and here I have plus 8 coulombs, and so negative charges will be more attracted to the right side than the left, and so some of the negative charges over here will end up being pulled across the conducting wire until they settle over on the right. There are several new terms that we can define here. First of all, let's just rename the two pieces of metal, A and B. We can say that there's a potential difference from A to B, which we symbolize with a delta V. In this case, it doesn't mean so much a change, but more a difference from one place to another. And a difference from A to B means we take the value of potential at B and subtract the potential at A. Again, difference from A to B, we always subtract the initial from the final. This is important. For example, in the scenario on our screen right here, B is at higher potential than A, and so delta V, the potential difference from A to B, is positive. And as we just established, electrons will flow towards higher potential, which means they'll flow in the direction of a positive potential difference. I can nonetheless write the potential difference from B to A, and it's just going to be the negative, right? If I'm increasing potential going one direction, I'm decreasing it going in the other. The term potential difference is a little bit of a mouthful, and it's such a common term. You'll see that we sometimes will use it 2 or 3, maybe even 4 times in a single sentence. So we give it a little bit of a simpler name just to make our lives easier. So we call potential difference the voltage. The term voltage is actually named after the unit of a volt. So the unit name came first, and then I think just to, again, simplify the language, eventually people started referring to potential difference as the voltage. Kind of like you might refer to the length of something as the footage. Which, complete tangent by the way, that's where the term footage, as in like video, comes from, because it's referring specifically to the length of the strip of film on which you've recorded your images. So the way I've phrased everything here is important. I've said the potential difference, or the voltage, from A to B and from B to A, and I've distinguished how they're different, that they're negatives of each other. But sometimes we don't actually care about which one is higher and which ones are lower. We really just care about the difference between them. In other words, I might not care which direction the charges are moving, I just care that they're moving. And when that's the case, rather than saying the voltage from A to B or B to A, I might say the voltage across A and B. Here I haven't specified a direction one way or the other. It's simply I care about the magnitude of the difference. And so if you see this terminology, what we really mean is the magnitude of the voltage from one to the other. Doesn't really matter whether I write it as from A to B or B to A, the magnitude will make it positive in the end, no matter what. We use this all the time as well. And so oftentimes we will write this as just delta V, where it's understood that this is simply a positive value. Given the context of the examples that we'll actually do and the problems you'll solve, it'll be clear when it matters and when it doesn't matter, or hopefully it will be clear. The other concept here that we're going to be using a lot of is this flow of electrons. We call this current, or rather specifically we call it the electron current. And we define it as the rate at which electric charge passes through our wire. In other words, if I put a little mark right over here, I would measure the current as counting up how much charge passes this one little section of my wire per second. So if I, run my stopwatch for 1 second and I see that 1 coulomb of charge passes through this one little section of my wire, that means the electric current is 1 coulomb per second. More generally, we represent the electric current as the symbol I, usually a capital I. Once in a while you might see it as a lowercase I. And we can write it as the charge per time, where the top is how much charge has passed through that part of our circuit, and time is how long we actually counted for. The units of current are coulombs per second, and we give that another name as well. We call this an ampere, and we usually represent it as a capital A. Current has a direction, right? The charges, the electrons are going in a particular direction. So we're going to add to our definition that the electron current is in the direction of motion of the electrons through the wire. There's something a little bit unsavory about all of this, right? Our electron current flows from A to B in this case. It flows from low potential to high potential. But I don't know about you, but it seems unintuitive that something should flow from low to high. If I think about gravity, for example, things flow from high to low. If I, pour out a tub of water on top of a hill, the water's going to flow downhill, not uphill. The reason for this discrepancy can be traced back to Benjamin Franklin. So when scientists were originally experimenting with this whole idea of current and electricity, they didn't really know what it was. They didn't have the concept of electrons. Electrons weren't discovered for more than 100 years later. Likewise with protons, that was even longer than that. So they knew that there was this concept, that there was this flow of something, and they knew that there was this concept of charge and that they could be opposites of each other, which they labeled positive and negative. And it was assumed by Benjamin Franklin that the charges that were moving, that were responsible for this flow of charge, were positively charged. And he was wrong, right? We know now that it's the electrons in most conventional circuits that are actually mobile, that are actually doing the moving. And so because he set everything up where it was the positive charges moving, once we discovered that it's actually the negative charges moving, everything kind of got flipped on its head. So when Benjamin Franklin did this, he said the current flows from high potential to low potential. But he was talking about what positive charges would have done. And positive charges would have done that. They would move from high to low potential, because high potential means more positive and low potential means more negative. And positive charges would like to get away from other positive charges and move towards negative charges. And in fact, this original convention of the flow of positive charges representing the current is still in use. And in fact, it's still conventional. And as such, we call it the conventional current. We symbolize it by the same letter I. It has the same units, amperes. The difference is that the conventional current represents the direction in which positive charges would be flowing through our wire. In other words, the conventional current points in the opposite direction as the electron current, but it actually has the same value. To understand why it's just a sign reversal, a direction reversal, let's look at this little example. So consider our atoms in our wire as blue boxes, positively charged blue boxes, and the electrons in our wire as little red dots. Now let's apply a potential difference to this wire with a low potential on the left and a high potential on the right, which will push the electrons to the right. In reality, the electrons would move all at once, kind of like water in a hose, right? The electron on the left isn't going to start moving before the electron on the right, really, or vice versa. They're all going to move along with each other. In fact, the one on the left can't really move to the right until the one on the right moves out of its way. But in some sense, the one on the left is pushing the one out of the right in the way. They basically move as one big conga line. But again, I'm going to represent this by moving the charges one at a time. I think it makes it a little bit clearer what's going on. When I move the first charge to the right, it leaves behind the positive atom. Don't worry about what's going on to the right of the wire for now. Then the next electron moves to the right and takes its place. And then the next one moves to the right and takes its place. And then the next one moves to the right. And the next one moves to the right. And the next one moves to the right. But was it the red dots that moved to the right? Or was it the blue squares that moved to the left? I mean, obviously, I moved the red dots. But in the end, if you go back and you rewatch that segment, you'll notice the empty blue square can be thought of as moving to the left rather than the red dots moving to the right. So the current, the flow of electrons moving to the right can be thought of as positive charges with the same amount of charge moving to the left instead. That's the difference between electron current and conventional current. The fact that conventional current is called conventional current is telling. That is usually what we mean when we talk about current. So if I ask, what is the current through this circuit, chances are I'm referring to the conventional current. One unfortunate piece of wisdom I can share with you is that the Regents physics exam uses electron current exclusively and refers to it as current. This is stupid because they're the only people in the world who do that. Everywhere else, the term current implies conventional current unless otherwise specified. All right, so let's summarize what we've learned so far, and then we'll move on to a couple quick examples. Current represents the rate at which charge flows through a wire, and it can point in the direction of the motion of negative charges or in the direction of motion that positive charges would move. The electron current, or the negative current, is usually representative of what's physically happening, but not always. For example, if you pass electrical current through mineral water, the ions in the water, many of which are positively charged, will also move. And so positive charges can actually move in some circumstances. We're going to deal with circuits that are made of wires and metal, in which case the positive charges are never really mobile. But it is worth mentioning that Benjamin Franklin didn't get it all wrong. There are, in fact, cases where positive charges do, in fact, move. While current represents the actual flow of charges, and therefore it represents electricity itself, what causes current in the first place are potential differences. So potential difference, or voltage, is what drives current. And in fact, conventional current flows from high to low potential, and electron current flows from low to high potential. Let's say I have a wire with a high potential on the left and a low potential on the right. Don't worry about what's creating it for now. And that there's a current of 10 amps passing through it. My question is, how many electrons have passed through point A in the wire after 1 minute of time, and in what direction were they moving? To find the number of electrons, first I have to figure out what's the total amount of charge that passed through point A. I can use the definition of current to figure that out. And I find that the total amount of charge that passes through any particular point on this wire after 1 minute or 60 seconds is 600 coulombs. It's worth pointing out that 600 coulombs is an absolutely monumental amount of charge. 1 coulomb is a large amount of charge. 600 coulombs is total. But 10 amps is a reasonable amount of current. And 1 minute is not a long time to have current flowing. So what's going on with this huge amount of charge? Well, there is actually tons of charge packed into pretty much everything. However, almost everything, or really essentially everything that we ever deal with, is almost electrically neutral, has almost as many positive charges as negative charges, or the other way around. There's only ever a slight imbalance in positive and negative charges. And in fact, if you took 600 coulombs worth of, for example, electrons, and you placed them on an object the size of your textbook, it would explode due to the repulsive Coulomb forces of all of those like charges so violently that you would probably take out the building that you live in. Anyways, so this is the total charge. To find the number of electrons, we can divide the total charge by the amount of charge per electron. And we get a whole lot of them. Now we have to figure out what's going on with the direction. This isn't something that we necessarily do mathematically, although in principle we can. In this case, I have high potential on the left and low potential on the right, and I want to know the direction that the electrons are physically moving through my wire. Well, we established that electrons kind of flow uphill in potential, and so my electrons are going to be flowing to the left. So I would say that this is my electron current. But if I were to ask you, without any other context, what is the direction of current through point A? The answer would be this way, to the right, because we would be talking about conventional current, unless otherwise specified. Or if you're taking the Regents exam, where it is specified that current means electron current. Sorry, not my fault. If you think it would be helpful, I think now would be a good time to take a break if you're feeling a little bit overwhelmed. This is a good stopping point for now. Otherwise, follow me to the next thing. Now that we've spoken about voltage and current, we can start to talk about actual circuits. In order to have a circuit in which electricity or current flows, I need to first have a source of voltage. One way I could do that is by doing basically what I did at the very beginning of this video, which is to set two objects with different amounts of charge near each other, and I can connect them by a wire like this. What I've drawn on the left over here, these two parallel lines, represents, for example, a parallel plate capacitor, which is essentially just two plates of metal that hold opposite amounts of charge. We've actually seen these before in our previous unit. Parallel plate capacitors are the things that we used in electrostatics to create electric fields that were more or less uniform between them. In a circuit, we use them for a slightly different purpose, but it is really the same object. This is not usually what we want out of our circuits. What's going to happen here is that the electrons over here, which are free to move, are going to repel each other away down towards the other side, which is also going to be attracting them because we've got this positive charge over here. And so the negative charges are going to freely move through this circuit until eventually the charge on both sides is balanced. There will be no more potential difference across our parallel plate capacitor, and there will be no more current. This typically happens very rapidly. So a capacitor is not usually what we want to use to power our circuits. There are exceptions. Because capacitors can discharge very, very fast, if you want to use a lot of electricity in a very short amount of time, this is usually how you do it. A good example of this is a camera flash. They produce an extremely bright flash of light, which means you need to get a lot of energy out in a very short amount of time, and that's exactly what a capacitor is good for. But it's not what I use to power my computer, or what you use to power your phone, or your switch, or almost any other electronic device that you use. Because if that were the case, this capacitor would discharge itself, and as it discharges itself, the voltage across it would go down, and as the voltage goes down, the behavior of our circuit would change, and I don't want that to happen. In order for my computer to run, it needs a fixed voltage. The way that we get a fixed voltage is through a battery. Batteries can look like a lot of different things. On the left, we have a conventional, maybe like AA battery or something. And on the right, this is more like what a car battery would look like. They look very different from each other, and the details of how they work can be different from each other. But for our purposes, they're the same thing. One end is held at a higher potential than the other end. So in a AA battery like this, one end will have a plus sign. Sometimes the other end also has a minus sign, or sometimes they just leave it off. But what that means is that the sign with the plus is at a higher potential than the side with the minus. Likewise, for the car battery example, we see something similar. You've already learned a little bit about how these things work when you took chemistry last year or the year before. You learned about salt bridges, you learned about voltaic cells. Well, that's basically the gist of what a battery is. Now, what makes a battery better than a capacitor? A battery is special because batteries provide a fixed amount of potential difference, a fixed voltage from one end to the other. And as you use it, the voltage doesn't change until you start to reach the capacity of the battery, and at which point it'll start to die and the voltage will change. A capacitor, the voltage across the capacitor will go down really, really, really fast. It'll kind of decay exponentially. With a battery, on the other hand, as you draw current from it, the voltage stays constant until you reach the end of its lifetime, in which case it kind of rapidly dies. This is more desirable for a lot of reasons. For example, my computer or most electronics require a certain voltage to operate. So a battery will provide a fixed voltage for a long time, and only when the battery starts to reach the end of its lifetime will the device finally stop working. With a capacitor, it might work for a little bit, but it's very quickly going to fail to provide what our device requires. So a battery is a device that provides a fixed voltage. I don't want to have to draw a Duracell battery every single time I want to put one in a circuit, so we use a symbol to represent it, and the symbol we use to represent a battery is this. It's 4 parallel lines alternating between long and short. There's a little bit of a rhyme to this reason, or reason to this rhyme, whatever. The side that has a long line is the high potential side, and the side with the low line, the small line, has the low potential terminal. And rather than writing out high and low, we represent high and low with a plus and a minus. Note that this doesn't necessarily mean that this is a negative potential and this is a positive potential. It simply means that in this case, the left side is held at a higher value of potential than the right side. Related to a battery is a cell, which you might see as well. This works the same way. It follows the same rule. The side with the long line is the high potential side. And the difference for our purposes is non-existent. Technically, a battery is only a battery if it consists of multiple cells. So you'll notice that the symbol for a battery is really the symbol for 2 cells sort of stacked next to each other. And if you think about what the word battery means, a battery of cannons on a battleship means a sequence of cannons, a whole bunch of them in a row. Battery in a criminal sense means like repeated beating, which is a little bit morbid. But nonetheless, the word means sort of a repetition of something. And so a battery is really just cells stacked together. Again, for our purposes, there isn't really a meaningful distinction between these two, but you might encounter the terminology, so I want you to be aware of it. In either case, a cell or a battery is something that provides a constant voltage, and the circuit elements are represented by 2 or more unequal lines. Note that for every long line, there should always be a short line. There should never be an odd number of these lines. So if I want to redraw my circuit on the left with a battery in it, it would look something like this. This battery will drive a current through this circuit. The current, the conventional current, will flow from high potential to low potential. And if I want to represent the electron current, it would simply flow in the opposite direction from low potential to high potential. This is a supremely useless circuit. In fact, all this circuit will do is discharge your battery. It will generate current, causing it to flow from one end of the battery to the other, causing the two ends to equalize eventually, and eventually the battery will stop functioning. Now, in this case, all the energy stored in the battery will be actually used to heat up the battery. And you can see this for yourself. If you have a AA battery or a D-cell battery or something lying around that you don't really need, and you can find a piece of metal that you can use to touch one end of the battery to the other, if you hold it there for a while, not even that long, if you hold it there for even 10, 15 seconds, you will probably, if the battery is good, you will feel the battery heat up. It's not dangerous. You're not going to blow it up or anything. It's not going to get so hot that you can't touch it. It's a kind of a neat demonstration. However, you should be aware that you are kind of wasting the battery. The longer you hold it there, the more the battery will discharge and the less useful it will be. A classic use of a circuit is to power something like a light bulb. You're probably doing that right now in your home. I don't recommend doing this because it can actually be dangerous between the glass and other potential problems. But if you actually take apart a light bulb, what you'll see is something like this. Here I'm talking about a traditional incandescent light bulb. They're becoming less and less common because they're not very efficient, but they are the easiest to understand. So what a light bulb is the following. You'll notice this metal sort of cylindrical thing over here, often called a thread contact or sometimes the sheathing. And there is this little black bit down here. This is an insulator. Then below that, you can't really see it in this image, but there's another little bit of metal. These two pieces of metal are a positive and a negative terminal for our light bulb, which means I can connect one end of a wire to this sheathing here and another end of the wire to the middle, and they are insulated from each other by this black material here. In the diagram on the right, that's what this yellow stuff is. It's an insulator. The wire that touches the outside of the sort of cylindrical part, the screw thread contact, travels up and around, and then it goes through this kind of coil of metal. It's almost always made out of tungsten because it has a very high melting point. It's very hard to melt tungsten. And this forces the current to flow through this tungsten coil out this other end, and then the current leaves through the bottom, or the other way around. It doesn't really matter. These can be hooked up either direction. So high potential could be here, low potential could be there, or the other way around. But this is what a light bulb is. It's a device that allows us to put current in one end, and we can take it back out on the other side. In the end, the reason why this produces light is the current that passes through this tungsten filament, for reasons that we'll talk about later, causes it to heat up greatly, and for reasons that we'll talk about even later, when things are very hot, they tend to glow. So now let's go back to our circuit diagram. And if I want to power this light bulb, I can insert it inside of my circuit like this. Where this circle with a squiggle through it is the symbol that we use to represent a light bulb. Now my battery is sending current through my light bulb. One thing to note is that if I were to hook it up like this, if I were to only only connect one side of my light bulb to my battery, nothing would happen. The reason why nothing would happen is because for current to flow across my light bulb, which is what I need to happen to make it light up, I need there to be a potential difference across my light bulb. But the way I have this drawn now, that's not the case. There's no potential difference. I've only hooked up one side of my battery. I need the other side too to have a difference in potential. Right now, everything over here is just going to be at some equal value of electric potential, and that's not going to drive a current. So I need to connect my circuit. This leads to some more terminology, and to make it a little bit more clear, I'm going to introduce a switch into our circuit. The way I've drawn this, our circuit is no longer complete. Again, there's no complete path. Current can't actually travel through the circuit because it needs a complete loop to do so. When the switch is like this, we say that the switch is open. When a switch is open, it means current can't flow. And that means the light bulb will be off. To represent a switch that's closed, we would either just represent it as a line, a wire, or we could represent it as the same way as before, but we would sort of connect it. So it's like this sort of triangular thing, indicating that now the switch has been closed. And if our switch is closed, current can flow through our circuit, and our light bulb will be on. This could potentially be a source of confusion for some of you, particularly some of you whose first language is something other than English. There are many languages that use this terminology the other way around. I should know. I grew up with a father who constantly said things like open the lights or close the lights, right? When he said that, he meant by open the lights, he meant turn the lights on. By saying close the lights, he meant turn them off. But in the context of a circuit, if I open a switch, it means I'm turning the light bulb off because I'm preventing current from flowing. If I'm closing a switch, I'm allowing current to flow, which means my light bulb will be on. So I know that Mandarin is this way. I think Bengali and maybe Hindi is this way. I'm not sure about Hindi. I know Bengali is. I know that in Hebrew and Arabic, those are all languages where the terminology here is a little bit reversed. So if this applies to you, I want you to make a mental note about this and try to avoid getting caught by that sort of language inconsistency. So what determines how bright the light bulb will be? If I plug in a different light bulb into the same circuit, I'm not always going to get the same brightness. Some bulbs are brighter than others, even though I'm not changing whatever is powering them. So what determines that? So one thing I think is probably clear is that if I have a stronger battery, it will probably make a brighter light bulb, right? If there's a greater voltage, if there's a greater battery voltage, it will drive a bigger current, right? A bigger voltage means a bigger push on the charges, which means we're going to get a bigger current flowing through our circuit. And if I have more electricity flowing through our circuit, I would probably expect my light bulb to glow brighter. This implies that there should be some kind of proportion between the voltage supplied by my battery and the current that runs through my circuit. And if there's a proportionality between these, it means there should be a constant of proportionality here. Some factor that determines, given a certain voltage, how much current will I get? Well, if this number is bigger, it means the same voltage will result in a smaller current. If whatever this constant of proportionality is smaller, it means the same voltage will result in a larger current. And so we can think of this constant of proportionality as something that represents how much our circuit resists the flow of current. This is really analogous to mass, where the voltage is like our force. It's what drives the current, just like force causes the acceleration, and resistance is what determines how hard it is for a particular voltage to drive a certain current, just like the mass determines how hard it is for a force to accelerate an object. Resistance is symbolized by the letter capital R. We can also look at its units, which by this equation above are equal to volts per amp. And this is given its own name. It's called an ohm. and it's symbolized by the Greek letter omega, right? Ohm, omega. And the equation here, which is usually rewritten the opposite way around, is called Ohm's Law. This is a super important equation. The entire unit of circuits is like 90% application of Ohm's Law over and over and over again. So we will be seeing a lot of this. But now we can go back and we can think about this light bulb. We already established that we presume that more current through a light bulb means that it'll be brighter. Well, in order to have more current through my light bulb given a certain battery, I need a small resistance. And so a light bulb with a smaller resistance will actually be brighter. Now, unfortunately, it turns out that light bulbs are a little bit complicated. So we're going to take a step back from light bulbs, and we're going to talk about a simpler kind of circuit element, which we call a resistor. And the symbol for a resistor is given by a zigzag. Although this is really only standard in the United States, in most of the rest of the world, the symbol for a resistor is a rectangle. This is what most resistors actually look more like. This, I think the rationale behind this is it's like sort of an obstacle for the current to get through. We're going to use this, but once in a while you might see this because some people just use the other convention. A lot of people use the other convention. So let's put this into our circuit. It might look something like that, where we have a battery with a voltage of, let's call it V, and we have a resistor with a voltage of R, and that means if I want to, I can use Ohm's law, and I can determine that the current through my circuit will be equal to the voltage across my battery divided by R. You might have noticed that I keep forgetting to put the delta in front of my V's for voltage. Voltage is potential difference, right? V means potential. So delta V means potential difference or voltage. But because in circuits, we almost always are talking about voltage rather than potential, most people get used to just leaving out the delta signs. I'm going to do my best to keep them in. I think at this point, it makes sense to keep track of when we're talking about potential versus when we're talking about potential difference. But once in a while, you might notice me slip up, and I might use a V to represent a voltage rather than just a potential. So just keep an eye out for that. I'm going to end this here, and we will pick up with more fun with circuits next time.